Okay, YouTube, in this video we're going to start our journey through the exploration of a particular class of function that we refer to as an exponential function. And so up until this point we've seen several different types of functions. Of course, we could represent them here, linear functions, something that looks like a line would be linear. Suppose we've seen quadratic functions that look like this U-shaped graph here. We've even seen absolute value functions, okay? Cubic functions, things that look like this. In other words, we have these functions that we recognize just by their basic shape and their basic properties because that they are used so often. We're just basically going to be looking at a new type of function that we refer to as an exponential function. And so the way we're going to do this or confront this is basically by taking a look at graphing a couple of exponential functions and talking about their basic properties and characteristics and see what we could say about them before we go through a formal definition. So when it comes to graphing functions, okay, you'll notice that we have two functions here, f of x and g of x. And it says here what we want to do is graph the following exponential functions by creating a table of values and then plotting the points. And then what we'll do is we'll just kind of create a smooth curve through the points from left to right and then kind of look at these two graphs here. And so you'll notice that these two functions, f of x and g of x, are a little bit different from what we've seen in the past though. What you're seeing here is that f of x, or in other words, I suppose we would say that that's another way of saying y there, f of x there, y equals 2 to the x power. Let's see if I can write on this here now. So we have y equals 2 to the x power, and here we have y equals 3 to the x power. So to make our table, let's recall that with respect to functions that are y as a function of x, we typically get to plug in whatever we want for x values here and then see what we get for y values here. So our domain values, I'm just going to start with some pretty simple ones here. -2, -1, 0, 1, and 2. And we'll do this on both of these here and talk about the behavior of these functions. But this is always a good way to see how a function might behave. So looking at this, we're basically going to go through and we're going to plug in these x values into our function and see what we get for y values. Now the interesting thing is, I'm actually going to request that we start by plugging in 0 into this function first. And so we would say that, 0, when we plug that into the function f of 0, this would be the same thing as 2 to the x power where x is equal to 0. Let's recall that when we take anything that's not 0 to the power of 0, we actually get a value of 1. So the first thing we're going to write here is that when we plug in 0 into this function here, we get 1. And that's another thing that I want to say about over here. As a matter of fact, if we were to plug in g of 0 right here, we would get 3 to the 0 power. We would also get 1. So one basic characteristic that we're going to see a lot with these exponential type functions is when you plug in 0, you get a value of 1. Now, proceeding with our 2 to the x example, if we were to plug in 1 now, f of 1, we would get 2 to the first power, which we would see gives us 2 here. And when we plug in 2, we say f of 2, we would get 2 to the second power, which would give us 4. So what we're seeing here is that every time x goes up by 1, we can see that what's happening is the right side of this expression is just doubling. Or in other words, what we're doing is we're really just taking 2 times itself another time. And so it makes sense that these numbers are going to double in nature. Now, if our x values were to get 1 less in value, would we multiply our y values by 2? Instead, what we would do is actually divide by this 2 right here. So one thing I do want to actually ask us to do is explicitly plug in -1 here. But talk about what we get. We get 2 to the -1 power, which if you remember from your rules of exponents, if you were to take this base and move it downstairs, okay, there's not going to be anything but a 1 left on top. But the moment you move that over that bar on a fraction, its exponent changes its sign. So we get 1 over 2 to the first, but in other words, we get 1/2. And that's kind of the idea of what I was saying before. If we were to go backwards here, we would be dividing by 2 to go the other direction here. So in other words, 1/2 is what I could take times 2 to get this 1 right here. And then also if we were to plug in, say, -2 here, we would get 2 to the -2 power, which is really 1 over 2 to the +2 power, which really gives us 1 over 2 squared, which is 4. So we get 1/4. So what we're going to do here is we're going to plot these points and talk about the shape of this graph, and then also some of the patterns that we're seeing over here on the right, and then what we'll do is compare it to this 3 to the x graph. So far, here's what we've seen. We see when we plug in 0, we get a height of 1 on this graph here of 2 to the x power. When we plug in 1, we're at a height of 2, so 1 comma 2 would be this point right here that's twice as high off the ground as the one before it. We see the point 2 comma 4, so 2 to the right, up 4 we see 4 is twice as high off the ground as our 2 was here, as high as our 1 was here. Now going backwards, -1, we're at a height of a half. And so graphing this, we kind of just, we draw right here, and then -2 comma a fourth would be this point right here. So in terms of drawing a smooth curve through this, I hope that as you're watching this, you're kind of getting this idea that if we were to continue to go upward here, 2 to the third power would be 8, 2 to the fourth power would be 16, 2 to the fifth power would be 32, that these points are going to just keep doubling and doubling and growing faster and faster, that our graph is just going to keep getting steeper and steeper. And conversely, going to the left side, if we were to go through this to the left, our graph would actually be flattening out and flattening and flattening and flattening and flattening. Now, one thing that's to be said about this, I hope that you're noticing that when we took 2 to the first power, we certainly got 2. But when we take 2 to the -1, we get 1 over 2. Or how about when we take 2 to the +2, we get 4, but 2 to the -2, we get 1 over 4. And so one thing that can be said is basically this: 2 to the -x, okay, let's just put it this way, any base to the negative power is always going to be 1 over the base to that positive power. So what we're basically saying is that, b to the -2 would be the reciprocal of b to the +2. And so to figure these out, b, if we would have plugged in -3 right here, we say, oh, what do you get? 2 to the -3. It'd just be the reciprocal of 2 to the +3, so we would get an 1/8. But you could see that if we were to keep going backwards, -4 here, we'd get a 16th. And I don't expect you to move your table this far backwards, but we get a 32nd. Essentially, we would see something where no matter how far to the left we go, we would always have something left over. So this is going to continue to get really close to the x-axis, but never touch it. So one thing we're going to add to our graph right now is an imaginary horizontal line here on the x-axis, and we're going to give this a name. Now, its equation is y equals 0, but we're going to give this the name an asymptote here, okay, is what it's called, a horizontal asymptote. And this, as we connect our dots now, I'm going to go ahead and do this. We're going to get it really close to the x-axis. Almost, it's going to look like it's on top of it. And as we continue to go to the right, we're going to keep getting steeper and steeper and steeper, even though we always can keep plugging in more x values to the right. And here's what we see, and we're going to label this graph. F of x equals 2 to the x power. So now, really quickly, let's look at 3 to the x power. Plugging these in, I suppose if we were to plug in g of 1, we'd get 3 to the 1 is 3, so we would get 3 here. If we were to, plug in a 2, we say g of 2 would be 3 to the 2 would be a 9. We could see we get a 9 here. And then going backwards, likewise, we could say g to the -1. Well, that's, that's the reciprocal of 3 to the +1. So in other words, 1 over 3 to the 1, we get 1/3. And then just knowing this pattern that exists here, we say, well, 3 to the -2 would be the same as 3 to the 2, but it's reciprocal, so we would get a 9th. And so graphing these, you can see this one's very similar in the fact that we still go through 0, 1, except for now when we plug in 1, we get 1, 3. So it would be, 3 times as high as the original dot, and you know what, higher off the ground than our f of x, because its base is just a little bit bigger. When we look at 2, 9, we would say 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 9 would be here. Now going backwards, we would say -1 would be at a height of a 1/3, which is already really close to 0. And then we would say -2 is a height of a 9th. And so the only reason that point right there, that 1/9, isn't actually touching the x-axis, even though it looks like it is because we're always going to draw in our horizontal asymptote and label its equation here. So this horizontal asymptote, again, this is just going to be this value for which our function is going to keep getting closer and closer to on the left, but never quite get to. And so I'm going to go ahead and draw this in here and say we have to put arrows on either side of this graph. Shame on me for not putting that over here. But this would be our graph of y equals 3 to the x. But already we can see some pretty basic common characteristics between these two exponential functions. So in terms of how are they similar, we could probably comment on their shape. And so we have similar shapes here. In terms of their behavior from left to right, are they increasing or decreasing? We would say that they both increase over their entire domain, okay? Entire domain. And that just means for all the x values that are in this function here, they're always increasing here, these two growth functions right here. And so in terms of what they have in common, what else do they have in common? They both must pass. And you can organize your writing a little bit better than I can here, but both must pass through the point 0, 1. And the reason behind that, and we're going to see this, is because if f of x equals some base to the x, the moment you try to plug in 0, we say b to the 0, we're always going to get 1. And so this is a truth about all exponential functions. And then the last thing we want to make sure we write here is that they both have a horizontal asymptote on the x-axis. Horizontal asymptote on the x-axis. So pardon me for organizing my work so poorly here, but I had to fit it in there somewhere. So in terms of how they're different, what could you say is different about these two graphs? I mean, they're very, very similar. We've listed 4 similarities between them, but how are they different? We could say that g of x, in terms of how it's growing, you could see that it kind of left our xy grid here a lot faster than our 2 to the x. So when we see something like 3 to the x, you have a bigger base, we're going to say it's going to have faster growth. So we say g of x grows faster than f of x. And we might make a comment here. This is due to the size of its base. And when we say the base, we mean the base of the exponent x, okay? So this would be our base is 2 here and base is 3 here. So for letter C, I want to know what are some of the characteristics of the graph of an exponential function. Well, some things that we can see here, and perhaps I could type a little bit faster than I can if it'll let me type here, then I can write. But we say basic characteristics of these graphs is we could see that all exponential functions would have to go through the point 0, 1. So all exponential functions of the form y equals b to the power of x must go through the point 0, 1. Let's see if I can fit another line in here. And all exponential functions, we'll write exponential growth functions for this one, increase more and more quickly across their domain. Okay, and I suppose we could say horizontal asymptote on x-axis. I just got to squeeze that in there. Okay, so that being said, let's take a look at letter D here. It says, is it possible for the graphs of f of x and g of x to have an x-intercept, and explain our reasoning? Now, when we talk about an x-intercept, we're saying, is there any x value which our graph would be on the x-axis? In other words, at a height of 0. And so one thing that I'd like to argue kind of through here is this. If we were on the x-axis, we would be at a height of 0. Then what that would mean is really we could say that our function, and I'm going to use f of x equals 2 to the x power here. We say f of x equaling 2 to the x is our example. We would say if y equals 0, then x equals what? Well, if we were to plug in 0 for our y value here, essentially what I want you to see is that there's never going to be a power of x that we could take 2 to the power of that we ever get exactly 0. And that's not to say we don't get close. As a matter of fact, we could see that if we were to continue to plug in more and more negative x values here, a -5, 2 to the -5 is 1 over 32. 2 over the -6 would be 1 over 64. -7 would be 1 over 128. That's just so close to 0. But you can see that this graph is never going to get to a height of 0. So when we say, well, why? Why does this happen? Essentially what we're going to say is there's no power of x that when we raise a non-zero base to it gives us a value of 0. A value of 0. Okay. So what is the domain and range of each graph? And this is kind of something we want to make sure we list here. But I think it's very clear after watching this here, or at least looking at these graphs, that the domain of all of our exponential functions, the domain, the set of x values for which our function is defined, is just all real x values. And the reason behind that is just because no matter what we plug in for x here, say for instance on these two functions, we can always take 2 to the power of that x or 3 to the power of that x. So for all exponential functions, we're going to say all real x values is our domain. Now, one thing we notice here about our range is that the only range values really that we ever hit were those that were positive, okay? And so we would say that y has to be specifically greater than 0, not greater than or equal to 0, because we have an asymptote on our x-axis. So before we finish up with this video here, basically let's take a look now that our general exploration is over. We'll take a look at our general definition of an exponential function and talk about its key points that you want to know going forward. So we say that the function f of x equals b to the x power, where b is greater than 1. So in other words, our base must be positive. So we'd say base, let me fix this here. Our base must be positive. Make sure that we write this. Try again. Okay, let's try this here. Not quite. The base b must be greater than 1. Greater than 1. And if that's the case, then what we're going to say is we have an exponential growth function. So I can't write on this, which is kind of annoying. But anyways, here's the thing. We're going to focus first on growth functions and then decay functions. But right now, what we want to say is that our base is some positive number bigger than 1. And so like 2 to the x, 3 to the x, 3.8 to the x. We say that this is the parent function for the family of exponential growth functions with base b. And so that this graph here that we see here has this general shape of an exponential function. Essentially, what I want to be able to draw for you is that all functions of the form f of x equals b to the x power, if b is greater than 1, are going to exhibit what we call growth. And they are all of them going to pass through the point 0, 1. All of them going to have a horizontal asymptote at y equals 0. So we're going to write HA for our horizontal asymptote. And then you'll notice that our one point that they also describe here on this graph that is really nice that they put this on here is here. And we're going to say that this is b, and this is the point right here, 1 comma b. So essentially, in terms of all exponential functions, since they all kind of have this shape anyways, what we're going to say is that we'll just memorize the parent function, and the parent function, there are 3 critical values that we always want to find here. So we say 3 critical graph values. And we're going to use these values to graph these going forward, but we would say that the horizontal asymptote, okay, x-axis. That's going to be one key characteristic of all functions of the form y equals b to the x. When we talk about other characteristics, we're going to say go through 0, 1. But more, generally I would say the y-intercept is what we want to find there, y-intercept. And then last but not least, we say goes through 1b. If you can find these 3 characteristics, then I'll accept any graph that you give me as long as you label those. So in terms of their shape here, we see this thing that never quite gets to 0 here, a height of 0. So we say an asymptote is a line that the graph approaches more and more closely but never gets to. We see that this graph rises from left to right, passing to the point 0, 1, and 1b. So the domain of f of x equals b to the x is all real numbers, and our range is just all positive values. So we say that if a is greater than 0, and b is between 0 and 1 here, then we're going to look at exponential decay functions next. So I suppose that's not of any importance right now. What you need to know is that any graph that has a base bigger than 1 to the power of x here, its basic shape is this growth function, and these are its 3 critical values that we use when we graph them. And that you can always make a table to graph these. Cheers.